Okay, let's continue. So we talked about Turing machine enhancements, the fact that it's the most powerful computation model we know, and let's talk about recognizability and decidability with respect to Turing machines. So a Turing machine can accept and halt, and it can reject and halt in either case, either accept or reject, and never run forever. And then the language recognized by it is said to be decidable, or Turing decidable. So a language is Turing decidable if and only if it's exactly the set of strings accepted by some always halting Turing machine. And for certain languages, we can certainly do that, right? For example, a regular language can be recognized by a Turing machine, in fact, by a finite automata that always halts. So for example, here are strings in sigma star, A, B, A, B, B, and so on. And here's what the machine does on these strings. On an A, it halts and accepts. So green means accepts, and it's a check, means yes, it's in the language. X means reject, it's not in the language, that's denoted by red. So the X's here are rejects, the check marks in green are accepts. So it accepts the string A and AA and AAA. So what's the language, just from this table, what's the language accepted by a machine that behaves this way? A star, right? So A star is therefore decidable, or Turing decidable. For shorts, we'll say decidable rather than mention Turing each and every time. You know, we owe him so much anyway, but we'll just say decidable. Okay, so A star is therefore a decidable language because it's accepted by a Turing machine that always halts. It never runs forever on any of these things. Okay, and that's a definition. That's what it means for a language to be decidable. Now, in a separate scenario, you can have a machine that accepts and halts, or rejects and halts, or the third scenario could be running forever. And running forever, whatever it is, it's not an accept, and so by definition we define it to be a reject, because it's certainly never accepted. It just runs forever, being undecisive. Right? So we equate running forever with a rejection simply because it's not an acceptance. So a Turing machine that has this property that it is allowed to run forever sometimes, and it accepts a set of strings. That set of strings is called recognizable, or Turing recognizable, because it's a set of strings accepted by some Turing machine that may run forever sometimes, and we construe that running forever is equivalent to a rejection because it's not an accepting state. So, for example, let's say the machine has this behavior. On an A, it accepts. On an AA, it accepts. On an AB, it runs forever. On a BB, it runs forever. On an ABB, it accepts and, rejects, rejects, rejects. So here are the accepts in green, the rejects in X's in red, and it runs forever as this forever symbol. And this still accepts A star, right? Except now we allow it to run forever on some instances. And you can think about running forever as a non-accept in a different way. It's a non-response. It's irresponsive to whatever it is that is happening with the machine, with that string. So non-responsiveness, no reply, is like a cold shoulder kind of analog of human behavior, right? If you send somebody a text and say, hey, what's going on? You want to do this or that? And you get no response. Whatever it is, it's not a yes, right? Whether it's in business or dating or friendships or whatever. So it's kind of a cold shouldery, passive-aggressive way of saying no is by not responding at all. So now we allow machines to have that property. You'll see very quickly that a lot of interesting results arise from this couple of simple, innocent-looking definitions. Right? So far, so good. So we define what it means to be a recognizable language and a decidable language. Decidable, machine always has to stop. Recognizable, it's allowed to reject by running forever and not saying anything. Okay. Omit the word Turing in front of these two terms. First theorem, every decidable language is also recognizable. Now, that's an easy one. How would you prove that from these two definitions? Every decidable language is also recognizable. Why is that true? Yeah. Yeah, if a Turing machine always halts, it's a special case of one that is allowed not to halt sometimes, because it's not a requirement, it's an option for it not to halt. Not to halt. So one that always halts is a special case of one that is allowed not to halt sometimes and halt other times. How many get that? So everything that's recognizable, everything that's decidable is also recognizable. But it turns out some languages are recognizable, but they're not decidable. It doesn't go the other way. These are two different definitions. Prove to me that this theorem is true. Some recognizable languages are not decidable. How would you prove that? What proof technique will you use, by the way? Counterexample. So give me a counterexample. Give me a language that you can recognize but not decide, not always halt and nail it. And I want other people to participate. So I'm already impressed with the 3 or 4 or 5 that are participating a lot, but let's get other people involved. And by the way, let's take a roll today. If somebody can pass a sheet around, just sign it, and we'll take attendance roll. Because remember, attendance is 10% of your grade. I want to make sure you get credited for showing up. So give me an example of a language that's recognizable and not decidable. I'll give you a hint. It's easy at this point. Well, do you know any languages that are not decidable at this point? Take a wild guess. What language is not decidable, not computable, no algorithm for, that we know of so far? In fact, we spend hours talking about it. Somebody say something before I start calling on people? Yeah. But there are no infinite strings in this class. But there are no infinite strings as far as we're concerned in this class. Strings are not infinite. A string is always finite. The length of a string is always a finite number of characters. Right? Sigma star has no infinite strings in it. Only has an infinite number of finite strings. Somebody help. How many understand my question? Just curious. Okay. What is my question? You tell me. A language doesn't accept strings. A machine does. So again, state the question succinctly. What is the question that I'm asking you? Yeah, find a language that is not decidable, but that you can recognize. Halting problem, thank you. Halting problem. We have a winner. So why was that so hard to say? I'm just a meta question. Why was that so difficult? I'm just curious. I don't know. All right. So the halting problem is not decidable. How do we know that? Well, we already proved it. Turing proved it. We proved it. End of story. Why is it recognizable? Why can you have an algorithm that correctly identifies all halting programs, and a non-halting ones, it rejects them through passively, aggressively not doing anything, just not getting back to us, not saying yes, and that's an implicit rejection. Running forever is implicitly rejecting. How would you do that in one word? Anybody but Keshab. You're not going to let Keshab have all the glory all the time, right? Simulation. What are you simulating? You're simulating a Turing machine that comes in the door. If it halts, you'll know, you'll say yes. If it doesn't halt, you'll keep simulating it forever, but you won't say yes, but you won't say no either. So you won't be wrong, And you'll be right an infinite number of times. In fact, you'll be right on all the yes instances that do halt. So you just recognized that language. How many get that? What does it mean to recognize a language? Right there. Language can be recognized. It's exactly the set of strings accepted by some Turing machine. So this Turing machine, the simulation, will accept exactly the set of strings that halt. It'll accept the halting language. The language made of strings that represent Turing machines that halt on their inputs. So technically speaking, it accepts machine input pairs separated by dollar signs or whatever. Okay. So the halting problem is recognizable but not decidable. So in other words, decidability is a special case of recognizability when you can accept all the yes instances correctly and the no instances you reject explicitly as opposed to running forever. Right? So in some sense, it's easier to recognize than to decide. The halting problem. It's easy to recognize. How? Simulate. It's impossible to decide. Why? Because it's undecidable. It's not computable. So it's not just hard to decide. It's impossible to decide. Impossibility is not just hard. It's not just really, really hard. It's not just extremely hard. It's impossible. That's worse than hard, right? I'm just saying. Okay. How many are with me so far? All right. This is going to get deeper very quickly. Anyway, your cartoons, your mileage may vary, but you can look at them on your spare time. Anyway, so a few more definitions. So an enumerator basically prints out all the strings in the language, all of them. In what order? I don't care. So you can easily have a machine, a Turing machine, or an algorithm or a program that prints out all prime numbers. Right? You print out prime numbers, and in fact, prime numbers, it's easy to print them in order. 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. So you can easily have a machine that enumerates certain languages like primes, perfect squares, Fibonacci numbers, whatever. So when a language has this property, there's a Turing machine or a program for it that does this, that language has an enumerator. That's an enumerator for the language. Okay. So here's the Turing machine with its tape. Here's the finite control, right? And it just prints out on its tape the strings in the language. In what order? I don't care. So it doesn't even have to be lexicographic order or smallest to largest. You get to choose. Okay. Arbitrary order. So if a language is decidable, it can be enumerated in lexicographic order. That's the theorem. So this enumerator can manage to print it out in lexicographic order. What does lexicographic order mean? Smallest first, and within size by lexicographic dictionary order. So lexicographic order is by size, and within size, dictionary order within the same size. All strings of size 3 will be printed out in dictionary order. So language, so now this is a theorem, it's not a definition. So we define what it means to be decidable and what it means to be enumerated. Now we're saying we have a theorem on our hands. It's not obvious. If a language is decidable, it could be enumerated in lexicographic order. How would you prove that? What's a proof for that? Why is it that if a language is decidable, it can be enumerated in lexicographic order and not just arbitrary order? Because Turing machines that halt cannot be enumerated in lexicographic order by size of machine or anything like that. It's impossible to do that. What do you say? Yeah. Generate all of sigma star, every single string from smallest to higher in size. Each one of them, feed it to the decider, because you already said you have a decider for it because it is decidable. So there's a decider that says yes or no on every string and in finite time correctly tells you whether it's in or outside the language. Generate sigma star in a loop. Send them all one at a time to the decider. Wait on the decider to come back for each one. If it comes back with a yes, you print it out. If it comes back with a no, what do? Move on to the next one. Don't do anything. Just keep going. And then you'd be a lexicographic order enumerator by calling the decider repeatedly on every single string, from smaller to higher. How many get that? It's a proof. It works. Okay. General. You can do it with Turing machines. You can do it with programs. You can do it in general. All right, so we just proved this theorem. Let's prove another theorem. If a language can be enumerated in lexicographic order, it must be decidable. You'll see where this is going, because lexicographic orderability, algorithmic lexicographic orderability, will coincide with decidability. So right now we proved half of it. Let's prove the other half, the other direction. If a language can be enumerated in lexicographic order, it must be decidable. Somebody else try to argue that, prove that. Why is that true? By the way, the third homework assignment has been posted. You got the email about that. There's a bunch of problem sets on the website from which everything will come. You know, homework problems, exam questions, midterm, final exam questions. So I worked long and hard on those problem sets, modified them, revamped them. They're all there now, and you should be looking at the problem sets, working groups, the usual stuff. Okay, why is the second theorem true? If a language can be enumerated in lexicographic order, it's decidable. Any thoughts? All right, go for it.
You can enumerate all possible things in either true or true enumeration, and you know that if it doesn't halt, then you know that it's undecidable. So you know that it halts.
What halts? So I'm trying to build a decider. So I'm trying to build something that says yes or no on a given string. And I don't know how to do this, but I have an enumerator as a subroutine. So how do I build a decider from an enumerator? Because before I did do the other way around. Right? I had a decider and I built an enumerator from it. Now I have to do the opposite. I have to build an enumerator from I have to build a decider from an enumerator. Before, I had to build an enumerator from a decider. How? By running the decider in a tight loop, run it on everything that you generate from sigma star. Here, you're doing the opposite. You have an enumerator in lexicographic order, and from it, you need to build a decider. So how do you do that?
Just check.
Check if what is where.
You have an input. You can just check is there in the order.
In what order?
In the lexicographic order.
And how do you get the lexicographic order? So start running the enumerator. Fire up the enumerator. It starts enumerating things in lexicographic order, but in comes in something you got to decide on. So I got to decide on this. All I got is an enumerator. So I'm running the enumerator. Now what? I'm building a decider. I can't use a decider. I am the decider. How do I operate? So I fire up the enumerator. Strings begin to spit out from the enumerator. What do I do? Yeah, it's a lexicographic order enumerator. So it'll start printing out the small ones first, the larger ones next, the larger ones still after those, and so on. So if a string comes in the door, I need to decide it. How do I decide? Fire up the enumerator. The enumerator will start spitting out lexicographic ordered strings that are in the language. I compare what I have to decide with each and every one string that comes out of the enumerator. If it's equal to any one of them, what do I do? Stop and accept. But what if it's not equal to any one of them, and an infinite number potentially coming out? As long as the strings begin to be larger than my string, I can stop and then reject. Either way, I stop. If I always stop, I'm a decider. That's what the decider is defined as, something that always stops. Right? It says either yes or no.
On the slide, you have the three different languages where some stop, some were accepted, some weren't accepted.
Yeah.
So recognizable continues.
So we're talking about this thing here?
Yeah.
Okay.
So is that's a recognizable language?
So this language here is recognizable because the machine sometimes halts and accepts, sometimes halts and rejects, and sometimes runs forever. And whatever that language is recognizable. Now, it just so happens that this language is also decidable using a different machine. This is the behavior of a particular machine. This isn't a property of this language. This language is an emergent property of how this machine M behaves on this particular string's W. Here's the W's. Here's the M on the W's, what happens. And here's the language of that machine based on where the green check marks are. You just made a type error. A machine is not decidable or not decidable. And my shoe is not even or odd. What is decidable? The language of the machine. I just want to make sure we nail that one tight. So decidable and recognizable are not properties of machines. They're properties of languages. So if there is a machine that behaves this way, the language of that machine has this property that is recognizable. The language is recognizable, not the machine. It doesn't make sense to say a machine is recognizable. Does that make sense? I'm sometimes not sure if I made something more confusing or less by answering a question. So help me out by asking more questions if necessary. So are we good? Okay. So we just proved a pair of theorems. If a language is decidable, it can be enumerated lexicographically. So here I built a lexicographic enumerator from a decider. How? Tight loop generates sigma star. Each one feed to the enumerator, and they will come out in lexicographic order. All the ones that the enumerator, all the ones that the enumerators will print are ones that the decider said yes on. And so the enumerator will be lexicographic ordering the output of the decider one at a time. How many get that? I probably use too many words to say it. Let me try it a simpler way. In the first theorem, we're building a lexicographic enumerator from a decider by calling the decider on everything in sigma star in order. The decider, what does it do? It always halts. How do we know? Because that's what deciders do, right? They never run forever, right? So it's decider always halts, either yes, always halts either with a yes or a no. Never with a I don't know or run forever. That's what recognizers do. They're allowed to run forever, right? Recognizers, right? Recognizers. So here are some running forever. So the first theorem is I built a lexicographic ordering from a decider. I built an algorithm to list the language in lexicographic order, given that I have a subroutine that's a decider. By calling the decider on everything in sigma star one at a time. Are we good on this? How many say, yeah, it's understood? Okay, any questions about that? Second theorem, the other way around. Instead of building a lexicographic orderer from a decider, I built a decider from a lexicographic order output. How do I build a decider from it? Something comes in the door, I need to decide it. I don't know what to do. So I'm going to run up the lexicographic order thing that spits out every string in order that is in the language. And I'm going to compare every string that comes out of this black box that's a lexicographic ordering machine with what I have to decide if it's in or out of the language. If any one of those is equal to that, I can compare things for equality. That's easy to do. I just accept and stop. How do I know when to reject? When the strings coming out in lexicographic order listing are larger in length, longer than this string I have, then I know, because in the lexicographic order, the strings will only get longer and longer and longer. They'll never be this size again. So I might as well stop running and say no, and I'll be right again. So now I've decided, based on a lexicographic ordering scheme that spits out strings in order. So if I have a small subroutine, a black box that spits things out in lexicographic order, I can build a decider from it. Point is, from each one of those, I can build the other. So if I have a black box that spits out lexicographic order, I can build a decider from it. And if I have a decider, I can build a lexicographic ordering algorithm for it that spits them out in lexicographic order, which means they're one and the same characterization. So the bottom line is a language is decidable if and only if it can be enumerated in lexicographic order. So we prove both directions. You see, it wasn't trivial to prove these two theorems, especially the second one. The first one was a little easier, even though that wasn't obvious either. I see some quizzical looks on your faces. Any questions about this? Yeah.
So, the enumerator has the knowledge of the language. It has some kind of algorithm to generate.
The enumerator has some algorithm that spits out strings of the language in lexicographically increasing order. Yes. How it does it, we don't care. It's his business.
It can't be like a database or something. It stores all the possible strings of
It better not store all possible strings. Why? Gave it a number of them. So how will it do that?
We don't care.
Well,
Magic column.
but it has to be an algorithm. And an algorithm is not magic. It's a bunch of lines of code. If you can do something with code, you don't need to resort to magic. And similarly, if you can do something with science, you don't need to resort to superstition. But I digress. So, if you have a black box that spits things out in lexicographic order, you can decide and vice versa. Let's take an example. Let's say I have a subroutine that can tell me if a number is prime or not. That's a decider for primality. How do I get an enumerator for primes using that subroutine? Generate all numbers. For I goes from 1 to, while true I++. And then what? Call the prime decider on each one of those. And if it says it's prime, print it out. If it says it's not prime, don't print it out. So I just build a prime enumerator from a prime decider. How many get this example? Really? Only half of you get that example? I mean, prime numbers? Seriously? How many see that I have a subroutine that can decide if something is prime? I can use it as a subroutine to come up with a piece of code that prints out all primes. How many can see that? Okay, that's better. Don't worry me like this. I mean, I get alarmed if half the class of smart graduate students can tell me to understand what a subroutine that prints out prime numbers is, right? I mean, that's disconcerting. Okay, let's do it the other way. Let's say I have a subroutine that prints out prime numbers in order, in increasing order. How do I convert that subroutine into a prime number decider? I need to know if a Google -9 is prime or not. And I have an enumerator for primes. I don't have a decider. I need to build a decider. Yeah. Run up the enumerator of primes, wait till it gets to a Google or so, and then see if one of those printed out is equal to a Google -9. And if it is, say it's prime. If it's not, if it gets to a Google +1, it ain't going to go to a Google -9 again because it's coming up in lexicographic increasing order. And then I'll know it's not prime. Either way, I can stop. And I'll be right. How many get that? Okay. By the way, is a Google -9 prime? How many say yes? How many say no? How many say yes? How many say no? It's undecidable? How many say it's undecidable? How many say it's an open question? Well, maybe open to you, but not to others here in the group. Open question must be open to all of humanity, not just you. Just because you don't know something doesn't make it an open question. Just saying, You don't get $1 million for solving that one, from the Clay Institute of Mathematics. So a Google -9, is it prime? Yeah, It's 10 to the 50 plus 3 times 10 to the 50 minus 3. How many see that? Yeah, it's a difference of squares, right? And Google is 10 to the 100. So 10 to the 100 minus 9, difference of squares, right? A squared minus b squared is a plus b times a times b. A plus b times a minus b. End of story. So we just factored a Google minus 9 without doing a Google calculations, divisions. And so presumably not. Maybe you can do a Google calculations really fast. Kind of doubt it. Not that fast. Okay, so we just built a prime decider from a prime enumerator. How many get that? Okay, any questions? So that's like a specific instance of these two general theorems. What we're saying with these two theorems, you can always do this, not just for prime numbers, for any language, not just the language of strings that are equal to prime numbers representation. It's a very general result. So what we're saying is you can always build a decider from a lexicographic enumerator, and vice versa. You can always build a lexicographic enumerator from a decider, conversely. It's always true. And we gave it, I still don't get the warm, fuzzy feeling that all of you get this. So you want to ask me more questions about this? Or are we good? We good? Okay. Yeah. Yes, we proved it generally. The prime number was an instance example of that. So you can kind of anchor it to something very concrete with primes. But it's true in general. If you can enumerate a language in lexicographic order and you need to decide an instance of that language, a string, take that string, comparing it to what comes out of the enumerator. At some point, either it'll be one of those and you can say yes, or what comes out of the enumerator will be larger in length than this string, and then you can say no. Either way, you can stop, and you'd be right. That's the general proof. And we did that with primes specifically, just to illustrate how it works. Okay. And vice versa for the other half of the theorem. No, I never said an enumerator generally is not lexicographic enumerator. Here's a prime number enumerator that's not lexicographic. 23. 5. 37. 3. Google plus 1. Actually, that's not prime either, but I'll let you figure out. You see, I jumped around. I didn't say, that's perfectly good enumerator. It's just not an enumerator in lexicographic order. Why is a Google plus 1 not prime? Actually, maybe it is. I'm not sure anymore. Anyway, the point is, enumerator is not necessarily lexicographic. A lexicographic enumerator is lexicographic. That's by size, and within size by dictionary order. But you can have a regular enumerator that's not lexicographic. Okay. But an enumerator must list every single string eventually. A string must eventually come out in an enumerator, not necessarily in order, but eventually, as opposed to never. One's not like the other. And of course, an enumerator must not list anything that is not in the language. That's also important. So you got to not just tell the truth, not just tell the whole truth, but tell nothing but the truth. Algorithms always have to satisfy those three conditions. They have to be correct, they have to be always correct, and never incorrect, if you will. Okay, 2 more theorems. Are you ready for that? If a language is recognizable, it could be enumerated by a Turing machine, not necessarily in lexicographic order. Now we lift the restriction of lexicographic order, and we end up with recognizability is the characterization of that. So why is it, if it's recognizable, it could be enumerated by a Turing machine in some order, not necessarily lexicographic? There's something about lexicographic order that makes it easier. And if you lift that restriction, just enumerate it in any old order, it's not decidable necessarily anymore, but it still must be recognizable. How would you prove that? So basically what we're trying to do, we're trying to come up with a enumerator from a recognizer. How many get that? That's what we're trying to do. We have an enumerator that we're trying to build, right? And so we have a recognizer, and we're trying to build from it an enumerator, right? How do we do that in a way that works? Uh, so it's recognized that there's a black box that recognizes yes instances. On no instances of the language, things that are not in the language, either says no or runs forever. I don't care which. But it doesn't say yes. So that's a recognizer. How many understand that? That's its definition. What a recognizer does, what a recognizer is. So we have a recognizer. How do we build an enumerator from it? The same as before. Let me just say that it's almost correct. But let's do it deterministically. So what am I trying to do? I have something that I can recognize. I can recognize the yes instances, always halt on the yes instances, always be right. I'm trying to build from it something that lists all the yes instances, like prime numbers. So I generate all sigma star in a tight loop, and each one of those I run the recognizer on. If the recognizer says yes, I print it out. But if the recognizer says no, I move on to the next one. Here's the tough case. When the recognizer keeps running and running and running and can run forever, what do I do? Do I print it or not print it? Do I list it or not list it? Is it in or is it out of the language?
You can just mark it and move on to the next one and then come back to it.
How many see the problem here? How many see the problem here? How many are listening to me? How many are listening to me? Are you guys listening to me? How many are listening to me now? Okay, that's good. If you guys are not responding, look, I can leave. We can all go home. We don't have to have a meeting. All right, so we have a recognizer. We're trying to build an enumerator from it. We can't just put it in a tight loop like we did before over here. We can't just enumerate sigma star, and for each one of those, feed it to the decider, wait on the decider, say yes or no, and then if it says yes, print it. If it says no, don't print it and move on. We can't do that. Why not? Because now this recognizer can run forever. It really means no, but it doesn't say no. It just gives you a cold shoulder and doesn't get back to you. It just runs and runs and runs. It doesn't make for a great decisive computation. It doesn't make for great human communication either. This cold shoulder, ignoring people, kind of, leaving them hanging. That's not great. But in computation, certainly, you can't convert that to a decisive yes or no. It's just not responding. It's running and running and running. So what do you do? How do you sidestep that and still have an enumerator? Because if it's running forever and you're waiting on it, you will wait forever too on that one string that it's churning forever on. And you'll never get to the next string, which can very well be halting in 1 second, and you'll never know because you'll never get to it. Because you're stuck on this thing that's running forever, and you're simulating it forever also. How do you break this cycle? What do you do? Yeah. Maybe. Yeah, what's the question?
Does an enumerator need to stop? Because it will be spitting out numbers in the
So
random
an enumerator spits out things in the language, strings in the language. Every string in the language will eventually be enumerated, and it will enumerate all of them. Now, if the language is infinite, it'll never stop by definition. If the language is finite, eventually it'll stop. Or let's just say print out the last string in the language. It doesn't necessarily have to stop, but it will print out that string. All strings will be printed eventually. And eventually doesn't mean forever. It means after a finite number of steps or time units, each string that's in the language will eventually be printed. Question?
So if it's longer than a string that's already been enumerated, just mark it and move on.
Yeah.
Come back to that.
Yeah.
So just to repeat that, I guess you
Yeah, it's good what you're doing.
His idea was the same, but that was deterministic, right? Because now you're
But it's not possible to come back. That's the problem. I'm not
Why is it not possible to come back?
because you will be enumerating. You will be trying to enumerating strings which are larger and larger and larger and larger. But at one point, you have to stop enumerating.
Yeah.
But you will not be stopping enumerating at the
So
same time.
so you, how about this? Use parallelism.
That is not deterministic.
All right. So let me explain several different ways. One is uh, take the first 50 strings and run the enumerator, run the recognizer on the first 50 strings for 50 steps each. Some of them will halt, some of them will not halt. Fine. Next, run on the first 51 strings the recognizer for 51 steps. Run it on the first 1,000 strings for 1,000 steps each. Run it on the first billion strings for 1,000,000,000 steps each. Each phase will finish completely terminate. How many see that? Eventually, I will run for enough time steps, the recognizer on every single string that exists. How many see that too? And they all have a chance to stop if they do stop. And when they do stop, I will print them out. So this will do the job. What technique did I use? Kind of slightly disguised here. One word. It's a simulation, but more fundamentally than that. What technique did I use here? Take a wild guess. Let me draw it for you. So string number 1, 2, 3, 4, 5, 6. So these are the strings in sigma star enumerated, listed out, numbered, right? I can do that. How many agree? Yeah. Okay. This is the time. 1, 2, 3, 4 time units for execution. So I'm going to simulate the first string for 1 unit, the second string for 1 unit, the first string for 2 units, the third string for 1 unit. I'm going to start simulating these strings for that many units, and eventually every string will be simulated for enough units that if that recognizer would halt, it will have a chance to halt. Eventually, how many see that? What technique is this now? Dovetailing. So meta question, why didn't you see it before I drew the picture, that it was dovetailing? Conceptually. So I use dovetailing not quite in this serpentine way, but I use dovetailing, in a more kind of a boxy way. I simulate everything here, then everything here, then everything here. That's still dovetailing. Remember, dovetailing has many guises. It can come in many forms. It doesn't always have to be a snaking path down a nice diagonal through in a big box. Right? Dovetailing is more fundamental than that. Right? All right. Yeah. Question. Yeah, but if the recognizer is running forever, that string is not in a language, by definition. Right? If a recognizer runs forever, it's not in a language. It's not one of those green, it's one of those red situations. Right? If a recognizer is running forever, that's equivalent to a reject. So yeah, we'll never see that it's running forever, but I will not print it out either, so I'm good. It's running forever. No, that's fine. I'm not going to print it, so I'm correct. Because it's never going to, it's running forever, so you'll never accept. So it's an implicit rejection. So I'm still okay. I'm not doing anything incorrect. Any other questions so far? Yeah.
So it can repeat, like it can print out more than once each string, or do you?
Yeah. So this will print out some strings many times potentially. How do you avoid printing out duplicates? You can avoid this actually. How would you avoid printing out duplicates? Just check or skip. Simple. How do you skip? What does that mean algorithmically, to skip or to check? Store all the strings that you printed so far, and every time you're about to print another string, first check if it's already been printed. If it is, don't do it. End of story. A Turing machine, where would it store all these strings? On a tape. How will it store it on a tape and still use the tape for more computations? Easy. Right, just do it in a different section of tape separated by a $sign, and don't let one mix up the other. That's all. It's like a program with two arrays. Right? So you can avoid duplicates. Very good question. Will the strings come out in lexicographic order? No. Depends how long the recognizer takes to recognize strings. The amount of time the recognizer takes to recognize a string has no relation to the size of the string, no direct relation in general. Very short strings can take an awful long time, and very long strings can take very quick time. How many can see that? Yeah. Let me describe another way to do this that's really equivalent to the first, but it sounds different. Run up a string through the recognizer, and while it executes, start running another string through it. And while both are executing, run a third string through it too with another thread. Create an extra thread every step. More and more strings, all the threads up to now are now executing in parallel. Whenever one of them accepts, print it out. And maybe check for duplicates. And then print it out. Otherwise, keep running all the threads simultaneously. Then you have 50 threads, 100 threads, a Googleplex threads. That's fine. We're not worried about efficiency here. How many see this is perfectly doable? Yeah. No, it's actually an algorithm. What you can think about it as a meta-heuristic, but it's an algorithm, pure and simple. Parallel execution. I don't have infinite parallelism at any point. How many can see that too? There's never an infinite parallelism. At any point, I'm only simulating 5 strings on 5 copies of the recognizer. Or I'm simulating 100 or 1,000 or a billion or a Google or a Googleplex or a Googleplex factorial, but those are all finite numbers. And eventually, everything that has a chance to halt will halt, and I will see it, and I will print it out, and I'll be an enumerator by parallel execution. How many see that this is sort of similar to this technique here? It's dovetailing again, disguised even worse than the other dovetailing. But it's still dovetailing, parallel execution. Your computer can run multiple threads. Right? How many realize that? Your iPhone can run, it literally is running dozens of threads at any given moment, even without any apps on it. With apps, it's even more threads. How does your one processor on your iPhone can handle all these threads all at the same time? Context switching or parallel execution. It's not really parallel per se, it's one processor, but it dovetails between them across time. It executes one for a little bit, and another one for a little bit, another one for a little bit, and goes back in round robins between the different apps or threads. And to you, it looks like they're all happening in parallel, but really they're all serialized like this in time. Okay. So parallelism can always be serialized. And that's a form of dovetailing too. How many get that last subtle statement? Good. Now you're getting it. You see why we harped on dovetailing so much. We talked about Cantor and infinite hotels. It's everywhere. It's in your operating system. Yeah.
Is this all possible because it's quantized?
Yeah, everything is quantized. Algorithms are, that's what they call discrete algorithms sometimes, because it's not continuous things like, continuous quantities like real numbers. But yeah, it's all quantized. But, more fundamentally, these things can all dovetail together, and you're doing a bunch at the same time. And if one goes forever, you don't care, because the others will not be starved for cycles. Whenever you have parallelism and mutual exclusion and contention, you have to worry about starvation, right? Starvation of processes for cycles. How many heard of that? You don't want that. You don't want a process or a thread to not get any attention from the CPU. On the other hand, if a thread wants a lot of attention from the CPU, like all of it forever, because it's running forever, you can't do that either. So you don't want to starve a process, but you don't want to let it hog up the CPU completely, because then others will starve. So you want to keep dovetailing, round-robining, however you want to think about it. Parallel execution, some sort of fair resource balancing with respect to computation cycles, whatever it takes. And so the point is here, you can't do this previous trick that we did earlier by enumerating sigma star and fitting them one at a time to the decider, knowing that the decider will eventually halt on each and every one and relying on that. Because now, sometimes this will not halt. And you still need to catch the ones that do. So you can't let the non-halting, forever running thread block all the ones that will halt quickly. Right? Just like a venture capitalist can't fund companies in serial. You can say, okay, you all want to start up? Fine. We'll fund yours first and wait to see what happens. And next, we'll fund his and then hers. That's not a good venture capital model. Why not? For a number of reasons. First, it'll take a long time, but never mind that. Let's not make time an issue. Yeah, I mean, he may flounder around for decades before he fails, or forever before, and never make a big profit, and just kind of flounder around and barely make ends meet and spend centuries like that. And this other guy will never get funded, even though he'll be the next Facebook or Google. We'll never know it. Same thing here. We can't just throw all of our resources into one instance and hope for the best, because it can go on forever. So you need some sort of parallel processing. Any other thoughts or questions about this? And you can explain it 17 different other ways, but the point is, you got to do something like that. Multi-threading, parallel processing. You call it non-determinism at the beginning. It's not incorrect to say that. But we don't need to bring in the firepower and the complexity of non-determinism per se. We can do this completely deterministically without invoking non-determinism, as if there's something magic about non-determinism that will make this work. There isn't. It's not necessary. So let's not invoke it unnecessarily and possibly obfuscate and muddy the water with that concept here. It's not needed. Again, Occam's razor in terms of explaining things. Okay, any other thoughts or questions? Now we're ready for the next part of the theorem, which is the other direction. And the other direction, we want to build a recognizer from an enumerator. So we have an enumerator and we want to build a recognizer for it. How do you do that? Yeah.
You know the enumerator will enumerate all possible strings in the language and then stop.
Well, if there's an infinite number of strings, it will not stop. So let's not use that word. An enumerator will just keep enumerating them and never stop, because it's an infinite number of strings.
But you know that recognizer can also run forever.
Okay.
So if it doesn't get enumerated, it doesn't get recognized. But if it does get enumerated, it is recognized.
Yeah. So basically, an enumerator will print out all the strings. So if you want to recognize something, fire up the enumerator. Just let it enumerate things. Things will be enumerated, not necessarily in order. But each time something comes up in the enumerator, compare it to something that you want to recognize. If it's the same, you can stop, accept, and not do anything else. And you'd be right. You'd be recognizing it as a yes. If the enumerator spits out more and more strings, none of them are equal to this, just keep going. Keep enumerating, keep comparing, keep enumerating. If it never comes out, you'll run forever with it. But now you're a recognizer. You don't have to stop. You can implicitly say no with a cold shoulder by not doing anything and just running forever. And that's okay too, because you're not accepting. And you're still a correct recognizer based on the enumerator that you're using as a subroutine. How many get that? Okay, any questions about that? So these two theorems say together that if something is recognizable if and only if it can be enumerated. The previous two theorems say that if something is decidable, it can be enumerated in lexicographic order. And those two are the same concept. They characterize the same set of languages. So again, decidability is the same as lexicographic ordering, ability. Okay? And recognizability is the same as enumerability in any order you want, not necessarily lexicographic. So we have two pairs of theorems that together give you two different characterizations of two different concepts, recognizability and decidability. And those are equivalent to enumeration in lexicographic order or just enumeration plain and simple, arbitrary order. 4 theorems, 40 minutes. That's okay. I mean, it could be worse. Any other questions, thoughts, ideas? Oh, yeah, it certainly is fun, right? But this helps characterize classes of languages in the Chomsky hierarchy. So remember the Chomsky hierarchy, we have regular languages, then we have context-free languages. This is a Venn diagram. Remember that diagram? Context-free around that, then decidable languages around that, then recognizable languages around that. So we just defined 2 more levels of the Chomsky hierarchy than we had before. Before we had regular, context-free. Now we have 2 more outside that. Soon we'll have plenty of others, and that whole big roadmap, will. I'm not sure where it is at this point. Anyway, that big Venn diagram, I can't find it right now, but it's probably 100 slides ago. And many other results will follow from that. So we're characterizing languages in this Chomsky hierarchy. Remember, that picture was basically the touchstone of the whole course, that big Venn diagram that I showed a few times and we'll show a few times again once we can find it at the slides. So this helps characterize things. Also, if a language is decidable, it's easier to recognize than if it's just recognizable. So if you know it's recognizable but not decidable, you're worse off. And it helps you understand the complexity of it better. And it's more challenging to handle one of these, than one of these. And it's certainly easier to handle a context-free language than a decidable language. And it's certainly easier to handle a regular language in terms of, as opposed to a context-free language. They get simpler and simpler as you go down the hierarchy, and they get more and more complicated as you go up the hierarchy. So it's kind of a map of complexity of things. So when you need to solve a problem in industry or for your thesis or for your job or for your company or for the government or whatever, if you first can classify it where in this hierarchy it falls, you have a much better chance of addressing it appropriately using the right tools and algorithms. And sometimes if you know it falls in a high enough class, complex enough class, there's no point in even trying to address it because it's so hard. So for example, if it's undecidable, don't try to come up with an algorithm for it because it ain't there. Save yourself the year of work and the embarrassment of failing. Not because something is wrong with you, but because it ain't there to be found. You can spend a year trying to find an integer between a quarter and a third, and you won't succeed in that either because it ain't there. So the more you know about this hierarchy and the different classes of languages and their relative complexity, the better off you are. As an algorithm designer, as a problem solver, as a system builder, whatever. It's very, very practical, actually. You'd be amazed how many people set out to solve undecidable problems, not realizing they're undecidable. They will, for sure, will fail. But they keep trying because they didn't know that. They didn't know about undecidability or Turing's work or diagonalization or the halting problem. And so they waste years of time and millions of dollars of their company's resources, and They come back and they said we couldn't do it. Whereas if they knew where in the hierarchy the problem is, if it's an undecidable region, they could have saved themselves all that trouble and money and embarrassment and opportunity cost. All right, so there's the alphabet alphabetized. Lexicographic order. Yeah.
In one of the previous slides, we built an enumerator for decidable.
Mm-hmm.
But can you give us an example of an enumerator without using decidable?
Well, you can enumerate certain things. For example, you can enumerate all halting programs. Go through sigma star, run every string in sigma star through the compiler of C compiler. When the compiler says it's a C program, then run that C program. Run all the other C programs in parallel, right? And when a C program halts, print it out. And now we have an enumerator that prints out all halting C programs. But we can't decide any one of them. There's no decider that decides all of them. We already know that because the halting problem is not decidable. But I just listed an enumerator for halting C programs. How many get that? Pretty straightforward, right? Question? That's why we do it in parallel. Right? Oh, the second theorem. So if it can be enumerated by a Turing machine, the enumerator keeps churning out strings that are in the language. That's what an enumerator does. It keeps spitting out strings that are in the language. So if I want to recognize some string that comes in the door, fire up the enumerator, and if it's equal to any one of them, I say yes. If it's not, I keep going. So now I'm a recognizer. I've just built a recognizer from the enumerator as a subroutine. Yes. Yeah. All I need to do is recognize the yes strings. The no strings, I don't care what I do with them. I just can't say yes on a no. I can't be wrong, but I don't have to be right on the no strings. I just can't be wrong on them by saying yes erroneously. So fire up the enumerator, checking against each one, and this whole thing taken as a big code is now a recognizer. Okay, let's move on. So more about decidability. So in the book, it's in page 150, 152, 153. There's enumerators and deciders and all that stuff is there. So you should read the book. Don't just rely on me for everything. So again, decider can accept or reject, but never runs forever. So the finite languages are all decidable. How many can see that? They're all decidable. Why? If the language is regular, it's decidable. Give me a decider. If I give you a regular language, how do you give me a decider for it? In particular, the Turing machine, what about the Turing machine? Yeah, finite automata. You don't even need the Turing machine. Take the finite automata and recognize that regular language. That's a decider for that language. It either accepts or rejects every string, and in fact, it'll decide very quickly. How fast will it decide on a string of length n? Linear time. Because it processes one more character for every state transition. At the end, it's either accepting or rejecting state. End of story. So the finite automata are deciders for the regular languages. That's a simple corollary of this theorem. Of course, finite languages are decidable too. That's a corollary of the regular language being decidable, because the finite language is definitely regular. If the regulars are decidable, so are the finite ones. But a finite language is even easier to decide. You can just have one big table with all the finite strings and then see if the input is equal to any one of them, and you say yes if and only if that's the case. End of story. It's a decider. Yeah. repeat that? Yeah. Yeah. In fact, this theorem proves that, right? That the regular languages are decidable. They're a subset of the decidable languages. Um, the context-free languages are decidable too. What's a decider for a context-free? The PDA. The PDA is a decider for that language. What if it's non-deterministic? It's still a decider, and if you want to make it deterministic, simulate it with a Turing machine. And then that's your decider that's deterministic. How many get that? Yeah, end of story. So we just proved three more, corollaries. I mean, I wouldn't even call them theorems because they're so simple, straightforward, right? Let me give you an intuition why it's so hard to decide and recognize. So if I say, let S be the strings x cubed plus x, y cubed plus z cubed for all x, y, and z, it's all numbers that can be represented as sum of three cubes, right? Pretty straightforward set, right? All possibilities, both negative and positive, x's and y's and z's. I say, is S infinite? What's the answer to that? How many say S is infinite? How many say it's finite? How many say it's infinite? Why is it infinite? Yeah, set y and z to 0, and the question is, how many cubes are there? Infinite. Of course, if you add y's and z's, it's even more possibilities, right? So definitely it's an infinite set. Contains all cubes and plus a whole bunch of other things. There are sums of cubes and triples of sums of cubes. All right, is it recognizable? If I give you a number, ask you, is it in the set? Say, is 13 in the set? Is 15 in the set? How many say it's recognizable? Yeah. Dovetailing. What does it mean, dovetailing? How will that translate to an algorithm? If I say it's 13 in this set, how does dovetailing tell you if it's a sum of three cubes? Enumerate all possible x's and y's and z's. In what order will you enumerate them in? Not any order. You're not going to say x is 0 and y is 0 and try all the z's. Increasing what? Increasing in absolute value. Yes.
So recognizability can still go on like
Yeah. So if a string is of that form, you'll say yes, because you'll stumble on the triple. That sum of cubes of that triple will be equal to that number. If it's not, you'll just keep going, and that's okay. Because now we're recognizing it, we're not deciding it.
So yeah, so if you go in any order, it doesn't need to be lexical.
No, it still can't go in any order, though. Because you can't say, I'll pick the order where the x is 0, the y is 0. First try all the z's. Then, later, after try all the z's with x 0, y 0, then try x non-zero or y non-zero. Because you'll never get to that. So you can't try any old order you want. It has to be, you have to make sure that you cover all bases after at least some amount of time, no more.
The same kind of parallelism.
Yeah, so when you dovetail, you can't dovetail in any order. You can't say, I'm going to dovetail this way and then come back, because there's no then after that, right? When you head down towards infinity, you ain't coming back from that. There'll be nothing after that happening, because it'll take infinite amount of time, which means you'll never be back to do anything else. So just be careful. Next question, is it decidable? That's a hard question, actually. All of humanity doesn't know it's decidable or not. Not only don't we know an algorithm to decide it, we don't know if one exists or not. It's an open question. It's been open for more than a century, actually several centuries. Let me show you a simple example of why it's so hard to decide. If I say, is 29 one of these things? Is 29 in S? What's your answer? How many say yes, it is? How many say it isn't? How many say 29 is in there in S? Why? Because it's 311. 3 cubed plus 1 cubed plus 1 cubed is 29. 27 plus 1 plus 1. So that was easy, sort of. Another question, is 30 in S? 30 is only one more than 29. How hard can it be? 29 was so simple. Yes, 30 is in there, but this is why. And I didn't believe it either when I first saw this, that this cube plus that cube is equal to 30. So, because I didn't believe it, I actually plugged it in. I don't have it here, but I plugged it into Google Calculator, and sure enough, that is true. Notice that some of them are negative, so when you cube it, you get a large negative number. So, the sum of these three cubes is 30, it turns out. It's exactly 30. All right, next question. Is 33 in S? This I won't bother you too much, because all of humanity doesn't know if that's true or not. It's been open for centuries. Actually, since the Greek times. The Greeks already knew about, this is that Diaphantine equation, right? Polynomial equation with integer coefficients. So we went from 29 to 30 to 33. From trivial to very, very complicated to nobody knows after all these centuries. From 3 small increments. You see, complexity explodes on you. It doesn't just gradually increase. And never mind, other integers. Who knows about those? Right. This is one of the questions of David Hilbert and Matiashevitz. Hilbert's 10th problem. They try to come up with an algorithm in general that solves Diaphantine equations. Tells you if Diaphantine equations have roots in integers or not. Very, very hard problem. So hard, in fact, it's undecidable. So Matiashevitz in 1970 showed that Hilbert's 10th problem, stated in 1900, was undecidable. There's no algorithm for it. Not even in theory. That means polynomials are as hard as Turing machine behaviors. In fact, polynomials can do arbitrary calculations, arbitrary Turing machine executions. They can simulate Turing machines. Polynomials can. That was a surprise. We didn't see that one coming, even after Turing and his results. We didn't realize that polynomials are robust enough, complicated enough, sophisticated enough to simulate any other computation that you can think of. So in some sense, you can have a polynomial playing with you World of Warcraft, at least in theory. I'm not saying it'll be a riveting game. It'll be very tedious. But the point is, there's a polynomial that does that. We'll leave it at that for now. So, closure properties of decidable languages. Just like we had closure properties of regular languages and context-free languages, now closure properties of decidable languages. Decidable languages are closed under union. How do you prove that? The union of two decidable languages is decidable. What's the proof? Not hard. Yeah, what do you say? Uh-huh. No, union. It's exactly what it says. So if it's in the language of the first machine or the language of the second machine, it's in the union. Yeah. You can OR them, essentially, basically execute both of them. And because decidable means they always halt, run the first machine on the input. If it says yes, then you say yes. If it says no, run it on the second machine. And if it says the second machine says yes, then you say yes. If either machine says yes, you say yes because it's in the union. Good, excellent, proud of you. So you basically simulate the two machines, right? You can either simulate the two machines together or in serial, one after the other, because they both halt, so you don't have to worry about any one of them running forever. Okay, how many okay with this? Good? Okay, good. Next theorem, the decidable languages are closed under intersection. Same thing, simulate both on the string, and you accept if and only if both accept, as opposed to one or the other accepts or both. Right? Simulation again. Third theorem, They're closed under complement. Again, pretty straightforward. And enumerate? Why we bring an enumerator into the picture? So language is decidable. Why is its complement decidable? And let's not involve enumerators here unnecessarily. You probably could, but it's a red herring. It's not necessary. Let me ask you, why are the regular languages closed under complement? Yeah, maybe leave it closed for a while. Leave it closed. No, I mean, don't open it. Close it and give it a few seconds. Why are the regular languages closed under complement? Yeah, do the opposite. Wait to see what the final automata do, and then do the opposite. If you accept, reject. If you reject, accept. End of story. Flip the final and non-final states, right? So why the decidable languages close under complement? Same thing. Flip the yeses to nos and the nos to yeses. It's decidable, so the machine will always halt and says yes, or it is in a language, or no, it's not in a language. Listen to what it says, and be contrary, and do the opposite. End of story. So that's why I'd rather not use enumerators here and make it more complicated than it needs to be. Just flip the answer. Flip the bit. Okay? Just negate. All right, decidable languages are closed under concatenation. So I give you a language is decidable, another language is decidable. Their concatenation is decidable too. What's the decider for the concatenation of the two languages as a function of the deciders for the two languages respectively? How do you build a decider for the concatenation of the languages if you have deciders for each? How do you use those as subroutines to build a decider for the concatenation? What's that? One after the other. Yeah. Simulate one and then the other on two pieces of the string. Which two pieces? A string comes in the door, you don't know where it breaks. Yeah. Every possible split. Try them all. You have plenty of time. Right now we're just worried about what's possible. Later in the course we'll worry about how fast the possible things can happen. That'll be even more complicated. Right now we're just worried about what's possible, what's not possible. So try all splits. And how many splits are there for a string of size n characters? N minus 1? N plus 1. How many say n plus 1? How many say something more? How much more? How many ways there to unconcatenate a string? I'm abusing notation here a little bit, but how many ways to split a string up into two pieces? So let's say I have string of 4 characters. How many ways is it to split it into two pieces? This way, this way, this way, live long and prosper. How many ways? I can either put the split here, 1, 2, 3, 4, 5. The first piece could be epsilon, or the last piece. So it's n plus 1, he was right. Nothing too more complicated than that. Try them all. So it's not even that many. Okay? So you guess factor or guess split the string by really trying them all. And then simulate the two deciders on each split, and then you'll know. Right? So we built a decider for the concatenation from the two deciders for the two languages respectively by running them in a loop on all possible ways to split a string up. This one is a little more involved. The clean closure, the decidable languages are closed under clean closure. How and why? Okay, and how do you come up with the factors? Let's not invoke non-determinism unnecessarily, because that kind of muddies the water. You see, people know non-determinism, then how do you do it deterministically? I don't know. I mean, let's not.
Non-deterministically, you can obviously translate to determinism.
Okay, then that's a little bit different. That's a little more disciplined. So non-deterministically guess where the split is into pieces. How many pieces? Any number of pieces that you'd like. For each one of those, run the decider on each piece. And if it accepts all the pieces, accept the original. But you used heavy non-determinism. So now you can take that construction and make it deterministic by running it through that Turing machine, non-deterministic to deterministic simulation, and you're doing it. But let's do all that without invoking non-determinism, because you could explain it without all that complexity. So you basically have to split up the string not into two pieces anymore, but to any number of pieces. So try them all. Brute force. Break it up into two pieces. How many ways? Two pieces? What he said earlier, n plus 1 ways. Now try three pieces. How many ways? I don't know, whatever it'll be. 4 pieces, 5 pieces, all up to n pieces. Try them all, run each case with all these pieces through the decider. And if one of them works, it's in the clean closure. So we just build a decider for the clean closure from a decider for the language itself. How many understand that? Okay, any questions about that? So it's the same strategy as before, except instead of 2 pieces, you have arbitrary number of pieces. But that arbitrary is not arbitrarily long, right? It's only as many pieces as you have, characters in the language, because you're not counting epsilons here. All right. So we did this closure property of decidable languages. Let's more quickly, do closure properties of recognizable languages. Same deal. So we just proved 5 theorems. Let's prove 5 more for the same price. So the recognizable languages are closed under union. Why? Simulate. But here you have to be careful. How are you simulating? Are you going to simulate it on one and then later simulate it on the other one? Parallel simulate. Yeah. It's important that you simulate in parallel here. Why? Because recognizer may not stop. But you're doing the union. So if one stops and one doesn't, and you're unlucky enough to simulate on the one that doesn't stop first, you'll never stop, and you'll never know that the other one stopped, and you could have stopped, but you'll never stop because you never got to the other one because you got dragged into infinity with the simulation that doesn't stop because you didn't do it in parallel. That's just what happens. Right? It's a venture capitalist that funds one company and later the other after the first one is done. That's not good business, and that's not good algorithms. Okay, recognizable languages are closed under intersection. Parallel simulation again. In fact, what about the parallel simulation? You don't need to do it in parallel this time. How many get that? Now you can simulate one and then the other. Why? Because if one accepts, it'll stop and no, and then you can simulate the other and wait for the other to accept, and then you can accept because both accepted, and you're in an intersection. But if one doesn't accept, that's okay. You don't have to accept, but you'll run forever, but it's okay, because running forever is not accepting. How many get that now? That parallelism is not necessary in here, although it doesn't hurt. If you did it in parallel, it'll still work, but it's not necessary. It was necessary in the first, but not in the second theorem. Third theorem, the recognizable languages are not closed under complement. This one is not so obvious. Why can't you just take the answer and flip it? Like we did with decidable. Because it can run forever. If you run forever, there is no answer to flip. What's the flip of running forever? Is it accepting? Well, if it is, then how do you know that you ran forever by running forever with it and then do something else like flip it? The flip will never come because you'll never know it runs forever because forever will never come, and so you'll never know. So you can't just run it and flip, because it can run forever. So that's a non-proof. It's an intuition that you can't flip, but it's not a proof. Maybe you do something else clever that does the same effect as a flip, but doesn't run forever. Maybe with some parallelism or non-determinism, who knows? How do you prove that the recognizable languages are not closed under complement? How do you know you can't enumerate? Maybe you can. Or show me an example of something that you could not enumerate. Let me ask you a more general question. If a recognizable language had a recognizable complement, then what? If a language was both recognizable and its complement was also recognizable separately, what can you tell me about these two languages? If there's a recognizer for the language and a separate recognizer for its complement, that language is decidable. Good. How many can see that? Why? That's true in general.
If it said yes on the complement, then you know it couldn't have terminated well. It had to have halted. So you're saying yes, so yeah, it has to say yes.
And one of the two must always halt. They can both say yes. One recognizes the language, one recognizes the complement. It recognizes the opposite of the language, stuff that's not in the language. So if you run a string through both of these machines, one of them will halt, and the other may do what it wants. The other can halt too and say no. That's okay. But they can't both run forever, because the string is either in the language or its complement. So one of them will eventually better say yes. Otherwise, it's not the correct recognizer. But it is a correct recognizer, because I told you the recognizer it recognizes that recognizable language. So by definition, it's a correct one. So one of the two will say yes. So run them both in parallel. One is guaranteed to say yes. When one of them says yes, abort the other, and then you'll have your answer, which is which. And you can say the yes or no. Now, you're a decider. You always halt. How many get that? Good. Any questions about that? So why do I say reduction from the halting problem here? If the halting problem we know is not decidable. How do we know? Well, we proved it. Turing proved it. We talked an hour about it. 2 hours probably. The halting problem is not decidable. What about the complement? But the halting problem is recognizable, right? How many get that? Right? One word. Why is it recognizable? One word. How do you recognize the halting problem? I hear a lot of words. I want to hear one word decisively answering the question. It's not hard. Simulate. Yeah. Run it. Test it. See what happens. Right? See what happens. That's 3 words. Run it. 2 words. Run. 1 word. Simulate. 1 word. That's a good word. The halting problem is recognizable. The complement of the halting problem is certainly not decidable. Why? Because if a language is decidable, its complement is decidable. We already argued that. Just negate, flip the bit. So the halting problem is not decidable, which means the complement is not decidable. But is the complement recognizable? No, it can't be recognizable either. Because if a language and its complement are both recognizable, they're both also decidable from what we said a minute ago. So the complement of the halting problem is not decidable and also not recognizable. So that's an example of something that is recognizable whose complement is not recognizable. So the recognizable ones are not closed under complement. So the halting problem is an example of that. More particularly, the complement of the halting problem is an example of a language that's not recognizable, even though the halting problem is recognizable, and one is just a complement of the other. So in some sense, the complement of the halting problem is worse than the halting problem, actually. Is more undecidable than the halting problem. Even though they're both undecidable, one is more undecidable than the other. They both are impossible to solve. One of them is more impossible than the other to solve, even though they're both impossible. How many get that? It's a very strict mathematical statement. It's not just Alice in Wonderland kind of play on words. So among impossible things, there are things that are more impossible than others, in a very strict mathematical sense. Another way of saying it, even if you had an algorithm to decide one problem, and you use that algorithm as a subroutine, you still couldn't decide the other, even though the first problem is still undecidable. By some magic, you had an algorithm black box for it, you still couldn't use that as a subroutine to decide the other. So the other is more undecidable than the first. So the complement of the halting problem is more undecidable than the halting problem itself. The halting problem is undecidable, sure enough, but it is recognizable. The complement is not decidable and not even recognizable. That's worse. You can't even recognize always non-halting programs when you see them, but you can recognize halting programs by simulation. But non-halting programs, there's nothing you can do to recognize those, not even simulation, and certainly nothing else. Because if you recognize non-halting programs, the halting problem will become decidable, because now the halting problem and its complement will both be recognizable, which means both are decidable. How many get this logic? Okay. Any questions about this? Yeah.
So in general, if you have to prove something is not recognized, we take a complement and reduce it to the halting problem?
Generally, you can do that or to some other undecidable problem, not necessarily just the halting problem. But yeah, that's a general technique. The recognizable languages are closed under concatenation, though. Why is that true? Why are the recognizable languages closed under concatenation? Yeah, split it right, into n+1 different splits, and run the two recognizers on each split. And if both of them recognize that split, you say yes. So could you do all the splits one after the other in turn? No, why not? Some of them may not ever terminate when others might, and so you've got to use parallelism here and try them all in parallel. That's okay. You can do that. So if there's a split that works that both say yes on, you can eventually simulate that in parallel with the other one, and that's the one that they both will say yes, stop, and agree, and then you'll know your answer. And even if the other ones runs forever or runs for longer, you don't care. You can abort the whole thing, and you got your answer, and you're a recognizer of the concatenation. How about under clean closure? Same strategy, except instead of two pieces, you have arbitrary number of pieces. Run in parallel the recognizers on all of it, the same recognizer on all the splits, on all pieces of all the splits in parallel, and then you'll know if one of them works and one of them does. So we just proved 10 theorems. 5 theorems on decidable closures, decidable languages closures, and 5 theorems on properties of closures of recognizable languages. That's 10 theorems in about half an hour. That's pretty good. That's like a theorem every 3 minutes. That's good timing. Good progress. And, in the book, we're chapter 5, going to talk about reducibilities next. So this is where we're going next time. Start reading ahead and look at the slide. How many are kind of reading in the book as we go? I hope it's all of you, and keep doing that. It's a good thing to do, especially some of the problems and the homework come from the book, so you almost have no choice but to look at the book and when you try to solve these problems. But next we're heading into this section here about reducibilities, and we'll get a lot of mileage out of this picture. This picture, looks innocent enough, but many, many theorems, a lot of interesting insights, and all of NP-completeness will arise from this picture. So pay special attention to these, section in the book, pages 206, 207, and so on. It's going to get deeper and deeper and more interesting and insightful as we go. Okay, any other questions or thoughts or issues with the homework? So we changed the deadline for the homework to a Saturday, right? You saw my emails. That means You don't have to submit the homework on Friday and then miss out on the opportunity of Saturday morning problem session, around noon with free pizza that I'm paying for. So it's due Saturday night, which means you can take advantage of the TAs on the Saturday with their wisdom and advice, and then submit it Saturday night if you have to. Wait that long. Hopefully, you should not procrastinate and submit things earlier, but okay. And solve lots of problems from the problem sets, and all the exam and homework questions will come from those sets. So do that. How many are working in groups, study groups? A lot of you, good. If you're not, again, you're kind of missing out on an opportunity to brainstorm, collaborate, and leverage other people's minds. You should do that. You should do a lot of it. It's always good to do. It's very empowering and productive to do that. Okay, anything else before we? The midterm will be after spring break at some time. I want to cover a little more ground. I mean, we could have it sooner, but let's cover more ground. Maybe have it right after the break. I'll announce some time. It'll be well, I don't want to be presumptuous. It could be a take-home or it could be in class, right? We have a 3-hour session, so you can perfectly have it in class. How many want an in-class midterm? How many want to take home midterm? Wow, I've never seen such a unanimous consensus vote. That's amazing. So, okay, we'll have it your way. So we'll have it, take home. And what I'll do is I'll have a calendar period where of multiple days, 3, 4, 5 days maybe, where you can work on the midterm for a chunk of time anywhere in that consecutive, say, 6 hours within a multi-day window, and you can pick and choose when exactly within that multi-day window you choose to take your 6-hour take-home exam. And of course, everything is time-stamped through Colab, so make sure it's no more than 6 hours. But you get to choose when, so you can schedule it against around your other commitments and obligations and midterms and due dates and so on. So I give you that option, no extra charge. My gift to you. Anything else for now? All right, another good session. We'll see you next week. Yeah. Sure.
Want to take the update on what I've been doing.
Okay. Let me